So Dr. William Rieken holds an advanced degree as a Doctor of Science, Computer Visualization at Tokyo University, Computer Graphics, Lisp, Computer Languages, Digital, Electronics, Nanomaterials, Superconductors, and Internet Security at Ryoko University, Nuclear Engineering with Computer Apps and Internet Security at Osaka University, Artificial NN with Applications in RoboCat at ATRI in Kyoto, and many, many more. In fact, his resume just goes on for so long that I can't read it all. But he has also held non-university positions. I've known Will for probably over 15 years now. He has also owned companies and done tons and tons of research. So he's going to be talking about today MHD and superconductors. And without any further ado, I would like to hand it over to Dr. William Rieken. Okay, and Will, it looks like we lost your audio, actually. Okay.
Is that okay?
There we go. There we go. Yeah, for some reason it asked me to merge audio. I'm not sure why, but yeah, looks like you're fine now, sir.
Yeah, it's kind of strange because
actually your audio sounds better. So whatever I did improved the quality.
Yeah, my cursor disappeared.
Oh, no, I can see that, and I can see your presentation as well. So I will mute myself out. And again, thank you for presenting and for your patience, sir.
No problem. Let me see. So as my dear friend Gary Stephenson had done MHD Propulsion about a month ago, Tim had asked me to do a presentation, and I thought I would follow up on what Gary had presented early on. So I'm not going to cover the same things that Gary did. What I'm going to do is look over MHD in general at the MHD component level and explain what is actually a MHD. So, yeah, so some background. So MHD is power is classified in two types, either AC or DC magnetic fields. The biggest difference is that AC does not require to be directly conducting of the fluid traveling through the field, whereas DC requires a direct connection to the fluid in order to operate. So you can look at MHD in two ways. One, in the external field, which is quite large, or two, as an internal field, which is smaller but more focused. So the problem of the external field is that, let's say you make a vehicle out of a MHD vehicle with the external field, then you're collecting metal as you travel along. Whereas if you have an internal field, you're able to control the structure of the field. And therefore you don't have any magnetic disruption to your environment, nor do you have any influence on machine devices that may be nearby. So magnetic fields in the superconducting sense have to be totally contained, because if they're not, then it's easy to, how should I say, um, it's easy to influence animals and or people who have electronic devices with large magnetic fields. So whether the field is external or internal, these type of precautions have to be taken into consideration. So the biggest problem with internal MHD is that the efficiency of the device is lower because you're directly interacting with the fluid that flows through it. So that has some effect on the field. However, because you don't have any leakage of the field, then this is a good reason to use that sort of design. So the other aspect of MHD is that whatever
we're not seeing the slides.
Yes, that's right. I'm trying to give a background.
Okay.
So the device that is made of designed for MHD should be a non-magnetic material. So what we will cover is what is, who is, and where from magnetic hydrodynamics. We'll look at open cycle, closed cycle, and MHD generators. MHD propulsion. I selected, since I live in Japan and actually have some connection to the Yamato, I decided to use that as the primary example of this talk. There were some experiments done in my laboratory to show MHD. I looked briefly at plasma propulsion, various reading materials. So MHD was discovered by Hans Alfvén, and he received the Nobel Prize in Physics in 1970. So magnetohydrodynamics comes from the way that the fields work in this type of device, where magnetic fields induce currents in a moving conductive fluid, which in turn polarizes the fluid and changes, uses the magnetic field itself to change the direction of flow. MHD, with a combination of Navier-Stokes and Maxwell equations, these equations are used simultaneously to solve for MHD problems. An ideal MHD assumes that the fluid has almost no resistivity, which is actually impossible, that it can be treated as a perfect conductor. Resistivity and kinetic effects are major limiting factors of MHD, as well as there are several material problems, which are a result of the wave modes, which include sound, Alfvén wave, and Magneto sonic waves. All of these have constant phase velocities for all frequencies. So in MHD, open and closed cycle, these are generally used for power generation. So we'll use the power generation as the example. So these plants are usually several thousands of meters in surface areas. So they're actually quite large, whereas the MHD component of it is actually quite small. Generally, these types of facilities don't use superconductors, although there are some cases where they have been used. You start out with coal, and with the coal, you seed the coal because coal is not a good conductor. So you add a seed, which goes to the combustor, which then air is compressed into the combustor so that it flows, so that the fluid flows through the MHD device, which then generates a positive or negative current, which is then passed through an inverter and outputs the type of energy that you're interested in. The particles then go through an air preheater, which then returns some of that air back to the compressor and starts the process all over again. Whereas the seed, which is actually quite expensive, is recovered and sent back to the coal grinder and re-implemented into the cycle. So there is some sort of reusability here. And the additional material is purified by nitrogen sulfate, and what's left goes out through the stack with CO2 gas. A closed cycle is very similar in operation than an open cycle. You can see very carefully here that it's very similar. The addition to the process is the fact that a part of the hot, instead of air, you have hot organopotassium in a sealed loop. So this introduces a preheater to the combustor to ensure that the temperature is proper, and molecular sieves to receive the argon or potassium that is used in the process. And that is then passed through a heat exchanger. Therefore, the MHD generator is now generating energy itself, as in the previous example, but it's also heating water that's coming from a lake or a river, and then turning the steam to drive a turbine, and in turn drive a generator, which actually these days may possibly be superconducting, therefore even more efficient. These type of systems, though, are still up to 80% efficient, depending upon their design. So, yeah, so one thing I wanted to also point out is that superconductivity has very little to do with these type of large systems, except that we can see here the north and south magnets, which are the actual superconducting component. So now we'll look directly at the superconducting component, which is again the north and the south magnets. A hot fluid passing through the electrodes, the anode and the cathode, and then generating the electric field. So we could consider this as we did in the previous example in a power plant, or we could consider in a propulsion system as well, where you have a plasma instead of a hot solid particle. So you have plasma instead, thereby generating a downstream energy moving a turbine or other type of mechanical device. So the superconducting ship, MHD Propulsion ship, the Yamato 1, was the world's first large-scale ship to be produced. The propulsion system was the idea of the Yamato 1 was a way to show the world that Japan had made it. Probably Japan's greatest failure was not to follow up on this technology. And therefore they conceded that to China now, which is now developing MHD propulsion for its warships. So, but as the interesting point of the Yamato was that it has because it doesn't have propellers, because it doesn't have propellers, it has lower noise, which is good for both devices inside the ship and also the surrounding marine life. So the Yamato now is in the Kyoto Maritime Museum, the Kobe Maritime Museum, which is not too far from where I live. The Yamato had 2 diesel generators to supply the electricity for cooling and thrusters and auxiliary systems. And just as we showed before, you see the water flow flowing between the electrode and between the cathode and anode. And you see the current being introduced, the magnetic field introduced, thereby the Lorentz force is now flowing by this simple equation of vector J by vector B. So the Yamato engine is quite interesting in that its engine had a saddle type arrangement, but the saddle type actually had in the top and the bottom halves, they actually had 2 saddles, top and bottom, to ensure that the forces would not blow apart the structure, but also have enough force to push the water through the ship. So the dual construction of the saddles themselves, 2 on top and 2 on the bottom, was actually an innovation of the time. So, and we can see again, magnetic field and current and results in force. So, however, one of the problems for the Yamato was that the engine was had to be constructed into multi-modules because they really needed 20 Tesla, which at the time was impossible. And so they realized they needed around 4 Tesla, but even a 4 Tesla coil would have been unable to be contained and would have exploded. So they decided, because these coils have 5,000 amps running through them. So what they decided to do was use niobium superconducting wire and make multiple versions of the same tube to use that for as a cluster rather than a single device, thus resulting in this design. So if you look closely, you can see that the superconducting saddles are here. And you can see that the propulsion electrodes, anode and cathode, are here. And here in the blue part, you see this is where the water flows through the system, from the front to the back. Here you see the entrance and the outlet. So this would be front and back would be the same. However, the liquid cooling was helium, and so they flowed the helium in the green portions, had radiation shields for the helium, and then vacuum vessel, and then the vessel itself. So this is how they were able to design the Yamato. So they had two of these engines, one on the left side and one on the right side. And together with 12 toroidal structures, sorry, not toroidal, saddle-shaped structures, then they were able to generate with 5,000 amps. Each coil was activated with 2,000 amps. They were able to generate enough propulsive force to travel, I believe, around 12 or 14 miles an hour on the open sea. So what I want to show now is some experiments that we did to demonstrate how MHD functions. For example, the Yamato. Here we have a copper coil, not protected like the Yamato was with a surface fiberglass. So I will try to. How do we play this? So you can see that the die goes through between the plates. And what you don't see here is the magnet. So I'm going to show that in the next slide. If I can, okay. Right, okay. So here is a magnet. This magnet is 0.7 Tesla, millitesla, sorry. 0.7 millitesla. And the dye will flow through it between the two electrodes. So that is a more clear experiment. Okay, and then I believe there is one more. So in the previous one, you've seen that the fluid flowed rather quickly, and this one rather slowly. We can control the velocity and the direction. Control the velocity simply by controlling the current. The direction can be changed from the front to rear or the rear to front simply by changing the polarity of the power supply. So in order So I had, our laboratory had developed some transparent nanomaterials. So I wondered if they would work. So I made this little experiment. So you see that there's no more copper here. These are actually nano surfaces. So we use the salt water. We use structural supports. That is this area here. And the magnets are 0.7 millitesla. The transparent material is a nanomaterial, which we have made. So the side view showing the transparent material. As I had tried to show before. In future work, the problem with the nanomaterial so far is that it's very short-lived. It lasts for about 1 second. So, or exactly one try. So future work would be to use transparent magnets around 1 Tesla, upgrade the nanomaterial, and use hydrogen air mixtures if we were considering flight applications. So now we'll show that. So yes, the current was too high for the nanomaterial that we were using, so it broke down. So which goes back to what I was saying before, upgrade the nanomaterial. So I wanted to highlight again an MHD engine for flight, one type of possibility. There's Vasimir, and there's at least another 4 or 5, perhaps even more, type of engine design. So it seems to me that utilizing plasma, probably hydrogen or air or oxygen or whatever. Again, it would have to be seeded. Cesium is actually one of the best seeding materials for a MHD engine for flight, although it is also highly radioactive. So not sure about the practicality of cesium. So the, again, superconducting magnets. And will we have superconducting plates for AC drives? That's a good question. So the main point is to somehow focus the plasma. So, and as I said before, there are already many ideas out there, and a lot of people working on exactly this type of proposal. So device, I should say. So the future of MHD, based upon what I've seen and based upon our own experiments, new nanomaterials to make them lighter, stronger, more efficient, higher magnetic fields. As I said, you know, we have 1 Tesla, 1 Tesla magnetic field, transparent magnetic field materials. These are in laboratories, not in the public domain. So and new ideas and new concepts. I remember Elon Musk when he started in rocketry. It was actually quite interesting. They either blew up or they kind of didn't work or kind of tried to leave the ground. But it was interesting because he was doing that while he was in college. And today, because he has new concepts, new thinking about how things work or how they can work. And I think also 3D printing and other new technologies helped him along the way. He is now the world's leading company in space technology as far as rockets are concerned. So will MHD reach a point where Vasimir and these other concepts will be useful? Let's hope so. And I put this one here because it was intriguing, simply because it seemed to have some of the characteristics of MHD. Doesn't mean it is MHD. It just means that you have a lifting body, you have some transparency, you have flashing lights, which to me look like pulsating, pulse drives, essentially. Probably using hydrogen because it's essentially invisible except in the IR region. So I put these together as is this the future of MHD? This is where it's all going? That's something that other people will, I'm sure, answer in the years to come. Reading materials, flying saucer technology. I picked reading materials that were related to MHD drives and other things. My good friend, Dr. Meyerbo, who invented the Lightcraft, uses a multimodal type of structure for his propulsion system, which includes MHD drive. So I don't know Bill Rose, but somehow he found out about my work in computer science and my patents and stuff like that. So, which I had built for my PhD in computer science. So I simply put Bill Rose's book out there, and you can read the patents as well. And I believe I do have a few papers on these. I was developing 360-degree vision aircraft for search and rescue applications at that time. Thank you very much. And I want to say thank you to Dr. Ateet and Gary and John for their overview. And of course, many thanks to my staff at my laboratory. They really helped a lot on the experiments and helping me gather things to put this presentation together. So that is I hope I didn't go too fast. Did I go too fast, Tim?
No, you did great. So Will, let me do this. Let me stop your screen share real quick.
Okay.
And I want to put this on gallery view. And everyone, please give a giant applause to Dr. Will Rieken, who has been at many, many, many events. Will, thank you so much for presenting finally. Thank you so much.